Okay, so we've started the recording. So today we have a presentation from Professor Halpern he's from the computer science department at Cornell University, professor in the computer science department, and the title of the talk is actual causality, a survey. So thank you, Professor, for coming. We're very glad that you accepted the invitation. Yeah. Sorry for the technical difficulties. I think you can start. Yeah.
Okay, thank you. Let me go full screen here. So this is to some extent an audience participation talk. It's not particularly technical. Don't wait to the end to ask questions. It might be too late. So this is a survey of work I've done on causality, which I'm still doing. The big picture is that defining causality is hard. Many approaches have been considered in the literature, and the philosophers have distinguished two kinds of causality, which they call type causality, sort of generic statements like smoking causes cancer, and token causality, the fact that Willard smoked for 30 years caused him to get cancer. So token or actual causality tends to be about specific instances, and type causality is more generic statements. I'll be focused on actual causality, and see a comment about what about one page at a time, but I'm not sure what that's about. Let me just keep going. And why should we care? Well, let's think of a statement like, it's true that it was pouring rain last night, and I was drunk, but the cause of the accident was the faulty brakes. So I'm suing General Motors. Typical American kind of thing to do. Now, notice that as far as type causality goes, well, drunk driving certainly causes accidents, and pouring rain would cause accidents. But we're claiming in this particular case, it was neither of the above. I drive great when I'm drunk. The cause of the accident was the faulty brakes. So what does that mean? So look, issues of actual causality are omnipresent in the law, like this one. Historians and scientists are concerned in causality. Statisticians are, and more recently, computer scientists have become quite concerned. So, as I say, my focus, at least for the beginning of the talk, is what does it mean for A to be a cause of B? And attempts to define causality really go back thousands of years. The modern view arguably dates to Hume. Hume actually gave two approaches. He didn't realize that. He gave one sentence, but it sort of encoded two approaches. And a relatively recent trend, which goes back to the philosopher David Lewis, uses counterfactuals. And the intuition is that A is a cause of B if it's the case that A hadn't happened, counterfactually, A did happen, but suppose it didn't, B would not have happened. So when I say the brakes are the cause of the accident, I'm saying if the brakes hadn't been faulty, even though they were, I would have had the accident. I wouldn't have had the accident. Does that make sense? So a more recent trend, which goes back to Judea Pearl, is to capture the counterfactuals using structural equations. So Pearl and I gave a definition of actual causality using structural equations. Well, actually, there are three definitions. The original definition appeared in 2001. Now, the problem with that definition and all subsequent definitions, I would love to prove a theorem that said, this is the right definition. I don't even know how to state that theorem, let alone how to prove it. So what we did in the original paper and all subsequent papers is to show how well our definition handled all the literally hundreds of examples in the philosophy literature that the philosopher used to shoot down other definitions. Now, the trouble with that approach is you leave yourself open to somebody coming up with yet another example that shoots down your definition. And that, in fact, happened. So a student of Pearl's, Max Hopkins, came up with a counterexample that we agreed was a counterexample. What does it mean to be a counterexample? Was a counterexample to a definition? Well, we're trying to define causality, and we all have intuitions about what causality means. And we agreed that this example, our definition said in the example, A is the cause of B. And I think most people, and certainly Judea Pearl and I, agreed that A should not be viewed as a cause of B. So our definition was getting it wrong according to our intuitions. So we improved, that is to say, we corrected the definition. That appeared in the philosophy journal, British Journal of Philosophy of Science. And then about 10 years later, I came up with yet another definition, very much in the same spirit, which I think is even better. And that's the one I'll be focused on today. So what makes this so hard? The trouble is the simple counterfactual definition, which, by the way, is what they use in the law, at least in the American legal system. If it works, we have a but-for cause. And everybody agrees that if you have a but-for cause, it's a cause. But sometimes you have causes that are not but-for causes. And here's an example. That this is due to David Lewis. Susie and Billy both pick up rocks and throw them at a bottle. Susie throws, let's say, a little bit harder. Susie's rock gets there first, it shatters the bottle. Now you can see, let's say you have video footage. The both throws are perfectly accurate. So that if Susie's rock had not hit the bottle, Billy's rock would have hit the bottle and shattered it. So we'd like to say Susie's rock is a cause, Susie's throw is a cause of the bottle shattering, but it fails the but-for definition because if Susie had not thrown, the bottle would have shattered anyway. Does that make sense? So we want a definition that generalizes the but-for definition. Okay, so we want to consider the case, well, certainly if Billy doesn't hit the bottle, if Susie hadn't thrown, the bottle wouldn't have shattered. So we want to keep fixed the fact. So here's the key to our definition. We're keeping fixed the fact that Billy doesn't hit the bottle, which in fact is what happened. Billy didn't hit the bottle. If we keep that fixed, then we get but for. We get if Susie hadn't thrown, then the bottle would not have shattered. So we have sort of a conditional but for definition, conditional on some fact that actually happened. If we keep that fixed, then we get but for causality. If Susie hadn't thrown, the bottle wouldn't have shattered. Now this is asymmetric. We can keep Susie fixed, but Susie actually hit the bottle. So we can't keep her fixed at not hitting the bottle. We can only keep her fixed at hitting the bottle, and then Billy's throw is not a cause. He didn't hit the bottle. As my kids would say, duh. How do we capture this? So the formal definition uses what we call structural equations. This is really due to Pearl, although its antecedents go back to the 30s. And the idea is that the world is described by, well, first we describe the world in terms of variables. The variables might affect each other, and the way they affect each other is modeled by structural equations. So formally, we split the variables into two sets, the exogenous variables, whose values are given, determined by factors outside the model, and the endogenous variables, whose values are determined by exogenous variables and other endogenous variables via the structural equations. So it's best to think of this as a DAG. It doesn't have to be. I have definitions that deal with circular causality, if you like. But for the purpose of this talk, Imagine a directed acyclic graph. At the top of the graph, we have the exogenous variables. Their values come from outside the model. Why did Susie and Billy throw rocks? I don't know. Some external factors cause them to throw rocks. And then the remaining variables are the endogenous variables. And for each endogenous variable, we have an equation. For those of you familiar with Bayesian networks, this is just like a Bayesian network, except instead of a conditional probability table, we have an equation. So are there any questions about that? All right.
What about circle dependencies between the variables?
Let me not worry about, so for the purposes of this talk, there are no such dependencies. I have definitions to, I solved the problem by saying it didn't happen. I do have definitions that deal with circular dependencies. It's the same basic idea. Now we have to look at fixed points. It's more complicated, and there's enough complexities, believe me, even without circular dependencies. And in fact, if you look at all the examples in the philosophy literature, they're all acyclic. I'm not trying to say circular dependence, if you have things like pressure and volume, does the pressure cause the volume? Does volume cause the pressure? Circular dependencies are interesting. You can unwind them if you're willing to talk about the pressure at time t causing the volume at time t plus 1. But in fact, even without unwinding, we have definitions that deal with them, but let me ignore them for this talk. I'm happy to say more about them if there's time at the very end.
Okay, I see.
So the formal language for reasoning about causality, we have primitive events like x gets 3. And we have, if you like, think of it as a modal operator. This talks about the effect of interventions. If I were to set x to 3, intervening and setting x to 3, then phi would be true. Now, the reason I have these arrows above the x is it represents a vector of variables. So if I were to set x1 to 3 and x2 to 5 and x3 to 4, then phi would be true. And then I close off under conjunction negation. For the purposes of this talk, I don't have nested interventions, although they're not hard to deal with. So formally, a causal model is a tuple that consists of exogenous variables, the ones at the top of the DAG, endogenous variables, and equations. And there's one equation for each endogenous variable. And the equation could be something like x is y and z. It can be a very complicated equation, but some equation. And the semantics is quite straightforward. Given that we're looking at acyclic models, once I determine the values of the exogenous variables, the ones at the top, I'm going to call that a context denoted by u. Again, it's a vector because there might be more than one. That determines everything else below it. So there's a unique solution to the equations once I give you the values at the top, because we have the equations, you can solve step by step. So I'm going to say it's true that y is 3. Given model M, remember model M tells you the exogenous variables, the endogenous variables, and the equations. Given this context, given the setting of the exogenous variables, y is 3. So that's straightforward. Again, here I'm using acyclicity. If I have a cyclic model, I have to look more at fixed points of equations. Whoops. Here's the interesting clause. What does it mean that after I set x to 3, phi is true? Well, the effect of setting x to 3 is to give me a new causal model. The new causal model, which I'll denote m x gets x, is just like the old one, except whatever equations I had for x are replaced by the equation x is 3, or if it's a vector, x1 is 3, x2 is 5, x3 is 4. So I intervened, I set x to 3. So you might have had an equation that said x equals y and z. Forget that equation, because now I've just set x to 3. independent of the equation, or x to 1 if it's Boolean. Does that make sense? So this is a new model.
So you just
Sorry.
instantiate some variables in structural equations, and that's how to say it, construct a new model. Yeah.
Exactly. Exactly.
Okay.
So, the nice thing about the structural equations model is it lets us model interventions. Now, note the effect of doing this in the DAG. If I set x to 3, it has no effect on the variables upstream. They're still determined by, the ancestors of x or the non-descendants of x. They're still determined by the original structural equations. Below x, things can change. You just set x to 3. So this will only have an effect on the descendants of x. All right, let me give you some examples so you get a feel for what's going on. So suppose we have two arsonists that drop limp matches in different parts of a dry forest, and both cause trees to start burning. We can imagine two scenarios. One I'll call the disjunctive scenario, where one match is enough to burn down the whole forest. It's very dry. The conjunctive scenario, you need both matches to burn down the forest. So if I was to model this as a DAG, I would have an exogenous variable. It determines ML1 and ML2. ML1 and ML2 is whether or not the arsonist drops a match. So, why do they drop a match? Due to some external factors, which I'm not going to model. So if you imagine U is a variable that is like 0, 1, it takes on one of 4 values. The first value, it's a pair. The first number is either 0, 1. The second number is either 0, 1. The first number determines whether the first arsonist drops a match. The second number determines whether the second arsonist drops a match. Now, the interesting clause is FB. Does the forest burn down? It's a function of ML1 and ML2. In the disjunctive scenario, it just takes one match. So ML2. In the conjunctive scenario, it takes both matches. So it's AND. So it's the same network structure, but different equations. So I still haven't defined causality. Let me define causality. So roughly speaking, formally speaking, I want to define what it means for A to be a cause of B. Whether A is a cause of B depends on the model and the context. So A can be a cause of B in one model context pair and not in another. So that means I'm giving the definition assuming all the relevant facts are given. I know the relevant equations. They're encoded in M. I know the initial facts that are true. They're encoded in the context U. And it's still not trivial to define causality. So I'm going to restrict, for the purpose of this talk, I'm going to restrict causes to conjunctions of primitive events. So a cause has the form x1 is 3, x2 is 5, x3 is 4. This, by the way, again, suffices for all the examples in the philosophy literature. Let me not worry about the fact that it's better thought of as a disjunction for now. But the phi, what can be caused, can be an arbitrary Boolean combination of primitive events. So again, there's no nesting here. So what's the formal definition? It has 3 clauses. The first and third are easy. The second is hard. So the first one just says, there's no way I would call A a cause of B unless it's the case that both A and B are true. Right? That's just not English otherwise. That if we say A is a cause of B, among other things, we mean that A actually happened, B actually happened. The only question is A a cause of B? But they must have both happened. So that's just AC1. AC1 says if you're going to call x gets little x, x equals little x a cause of phi, then both x has to equal x and phi has to be true. Let me jump to AC3. It's a minimality condition. it says if I'm going to call x equals 1 and x1 equals 1 and x2 equals 3 and x3 equals 5, a cause, the no subset is also going to satisfy AC1 and AC2. So I want to get rid of irrelevant conjuncts. I don't want dropping a match and sneezing to be a cause of the forest fire if just dropping a match is a cause of the forest fire. So AC1 and AC3 are really quite non-controversial. All the action is in AC2. I said originally, there are three definitions of causality. I'm going to focus on the third. All of them had AC1 and AC3. They differed in AC2. Let me give you the AC2 for the definition that I prefer. It's still a little complicated, but believe me, it's much less complicated than it used to be. And it's this notion of conditional, but conditional but for. So there's a set, again, exists. There's some set of variables W, endogenous variables. They're in V, those are the endogenous variables. And a setting X prime of the variables in X. Again, I'm trying to show that capital X equals little x is a cause. So I'm saying, well, if X were little x prime, then phi wouldn't happen, right? If you ignore the W, this is just but for causality. It's saying if X weren't X, if it were X prime instead of X, then phi wouldn't hold. But now I'm allowing conditional but for. I'm saying fix any set of variables to their actual values. Hold them fixed and conditional on that. If X is little x, then phi wouldn't have happened. So it's conditional but for. Right? The counterfactual holds that is, say, if X weren't little x, if we're X prime instead, provided the variables in W are held fixed. Does that make some sense? It'll be clearer, I hope, when I give you the examples. Any questions? So let's go.
It will be great if you have some examples.
Yeah, I'm going to.
Thanks.
Okay, let me give you the examples. So first, the arsonist. There's no W there. So in the conjunctive case, each of ML1 and ML2, each arsonist dropping a match is separately a cause. Each one of them caused the fire. It's but for. Had they not dropped the match, there wouldn't have been a fire. And that just shows that an effect can have more than one cause. Each one of them separately is a cause. Now, in the disjunctive case, the cause is the conjunction. We need them both to drop a match to get there to be a fire in the disjunctive case. If we change them both, in other words, for but for causality, if we call the conjunction a cause, we're allowed to change both. If neither one drops a match, there's no fire. But we can't just change one of them because one is enough for a fire. Now, it's interesting. I have a definition. This might seem a bit strange. I mean, that you need, so to speak, a stronger cause in the disjunctive case. Only one is enough, but the conjunction is the cause. And it turns out I have a definition of sufficient causality. For sufficient causality, it's just the opposite. In the disjunctive case, each one of them is a sufficient cause, and the conjunction is a sufficient cause in the conjunctive case. So that might seem closer to your intuitions, but I will say that the law is interested in actual causality. The law would say, at least American law, each one of the arsonists was enough to cause the fire. Each one is individually to blame. They're the cause. In the disjunctive scenario, you need both of them, and together they're the cause. But again, there's no W here. A more interesting case is the rock throwing example. So if you had a naive causal model with just three variables, So I'm ignoring the exogenous variable. So I'm ignoring what causes Susie to throw and Billy to throw. But imagine they both throw. Then the bottle shatters. And you can imagine an equation says, okay, that we build in the fact that they never miss. So the equation for BS is just ST or BT. And then they're both causes. It's completely symmetric. And that's not capturing the story. It doesn't capture the fact that Susie threw a bit harder. So here's one way of capturing the fact that Susie threw a bit harder. So let's add, there's more than one way, by the way, but this is one. Let's add variables SH and BH for Susie's rock hits the bottle, the intact bottle, and Billy's rock hits the intact bottle. So now we have a picture like this, and let me bake in the fact that Susie hits first. So if Susie hits, then Billy does not hit. That is to say, the equation for Billy hits is Billy hits if Billy throws, and Susie does not hit. Because if she hits, she got there first. She shatters the bottle, not Billy. So I didn't write down the equations, but I hope they're clear. Susie hits if Susie throws. Billy hits if Billy throws and Susie doesn't hit. And again, the bottle shatters if either one of them hits. Now, Susie's a cause. Why? Because we can take W to be BH, fix BH at its actual value, which is 0. Billy didn't hit. If we fix that, then if Susie doesn't throw, then neither one hits the bottle. Then the bottle does not shatter. Whereas if she does throw, even if Billy doesn't hit, the bottle does shatter. So we have a but-for cause. So Susie throwing is a but-for cause, conditional on Billy not hitting, which is what happened. You can't play the symmetric game to make Billy a cause, because you can't fix Susie and not hitting. She actually hit the bottle, right? So you can test, any way of fixing the variables, but you can't make Billy the cause. Only Susie is the cause here. Does that make sense? Are there any questions? All right. Let me give you some other examples to show you how this might be counterintuitive. So this is due to Ned Hall, a philosopher at Harvard. Billy contracts a serious but non-fatal disease. He's treated on Monday, so he's fine on Tuesday. Had Monday's doctor forgotten to treat Billy, Billy's doctor would have treated him. So you have to imagine there's an equation where Tuesday's doctor checks the chart. If Monday's doctor treats him, Tuesday's doctor doesn't. If Monday's doctor doesn't treat him, Tuesday's doctor does. And if Tuesday's doctor had treated him and Monday's doctor had not treated him, Billy would have been fine on Wednesday. Would have been sick on Tuesday because Monday's doctor didn't treat him, but he's fine on Wednesday. There's a catch. These are philosophers. 1 dose of medication is harmless. 2 doses are lethal. So if both doctors treat him, he's dead. So we might ask, is the fact that Tuesday's doctor, so in fact, Monday's doctor treated him, Tuesday's doctor did not. Is the fact that Tuesday's doctor did not treat Billy the cause of him being alive? And the answer is yes, he's a but-for cause. Had Tuesday's doctor treated him, given that Monday's doctor treated him, he'd be dead. So let's formally model this. We can imagine 3 variables. Monday treatment, Monday's doctor treated him, yes or no. Tuesday treatment, Tuesday's doctor treated him, yes or no. And Billy's medical condition, that's a variable that has 4 possible values. It's 0 if he's okay Tuesday and Wednesday morning. That is, if Monday's doctor treats him and Tuesday's doctor does not. He's sick on Tuesday morning and okay on Wednesday. That's if Monday's doctor doesn't treat him and Tuesday's doctor does. He's sick both Tuesday and Wednesday. That's if neither doctor treats him. And 3 is that he's okay on Tuesday and dead on Wednesday. That's if both doctors treat him. And I'm hoping the equations here are obvious. But again, we assume the equation for TT is that Tuesday's doctor treats him. The equation says that Tuesday's doctor treats him exactly if Monday's doctor does not. So what can we say about causality? The fact that Monday's doctor treated him is a cause of Billy being okay both Tuesday and Wednesday, and of Tuesday's doctor not treating him. It's a but-for cause, because had Monday's doctor not treated him, Tuesday's doctor would have, but then BMC wouldn't be 0, it would be 1. He'd be sick on Tuesday and okay Wednesday. So MT1 is a but-for cause of both BMC being 0 and TT being 0. TT being 0 is a cause of Billy being alive. Well, I take alive to be BMC's either 0, 1, or 2, not dead, not 3. Because if Tuesday's doctor had treated him, given that Monday's doctor treated him, he'd be dead. But here's the interesting thing. Monday's doctor treating him is not a cause of him being alive. Because if Monday's doctor doesn't treat him, no matter what else you hold fixed, he's going to be alive. The only way he's going to be dead is if Monday's doctor treats him and Tuesday's doctor treats him. So it's easy to see that Monday's doctor treating him can't be a cause of him being alive, because there's nothing you can keep fixed so that if you change MT to 0, Billy's dead. If MT is 0, then Billy's alive for sure. Again, does that make sense? But what that tells you is that causality is not transitive. If we take A to be Monday's doctor treats him, B to be Tuesday's doctor doesn't treat him, and C to be he's alive on Wednesday, then A is the cause of B. Monday's doctor treating him is a cause of Tuesday's doctor not treating him. B is the cause of C. Tuesday's doctor not treating him is a cause of him being alive. But A is not a cause of C. Monday's doctor treating him is not a cause of him being alive. Now, this might seem quite counterintuitive. It certainly did to me. I always thought of causality as being transitive. There are quite a few examples now in the literature, in the philosophy literature, in the spirit of this one. And I think philosophers by and large agree that causality is not transitive. That still leaves us with a puzzle why we think it's transitive. For what it's worth, I have a paper that gives sufficient conditions for causality. And I try to make the argument these are the ones that arise most of the time. To some extent, you can debate whether that's true. To the extent that it's true, that at least might explain why we think of it as being transitive, because typically it is transitive. Now, the interesting thing is Lewis, in a very influential paper, gave a definition of causality, but in his definition, he sort of bakes in transitivity and right weakening. Now, by right weakening, I mean if A is a cause of B, and B implies B prime, logically implies, then A is a cause of B prime. We don't have that either. MT is a cause of BMC being 0. That is, Monday's doctor treating him is a cause of him being okay Tuesday and Wednesday. BMC being 0 certainly logically implies the disjunction, but MT is 1 is not a cause of the disjunction. So A implies B, A is a cause of B, B logically implies B prime, but A is not a cause of B prime. And I say Lewis assumed that it was, and most philosophers, I think, at this point say that that's simply incorrect. All right, some more interesting examples. This is due to Josh Snow. I don't know who Fraser is. Josh is a professor of philosophy at Yale, but he has an appointment to the cross appointment to the psychology department. He calls himself an experimental philosopher. He does experiments. And here's one he did. The receptionist in the philosophy department keeps her desk stocked with pens. The administrative assistants are allowed to take the pens. In practice, faculty members are supposed to buy their own, but in practice, they both take pens equally often. On Monday morning, both an assistant and Professor Smith take pens. Later, the receptionist needs to take an important message, but there's no pens left. Who's the cause? Now, according to our definition, both the assistant and the professor are but-for causes. Had they not taken a pen, there would have been a pen there, and the receptionist could have taken the message. But if you do the experiment, you'll find that most people say Professor Smith is the cause. Why? Well, what Noah postulated is he broke the rule. Faculty members are supposed to buy pens. He didn't. So he did something quite abnormal, which in practice wasn't so abnormal. Statistically, both admins and faculty members take pens. So people blame him or her. And he tested this by saying, suppose we change the rules. It says the pens are supposed to be for faculty members. Administrative assistants get pens some other way. And now everybody says the cause is the administrative assistant. So clearly, people are influenced in making their decisions by more than just the structural equations. And in fact, this observation goes back to Kahneman and Tversky. Kahneman won the Nobel Prize for economics, and Tversky would have won it as well had he not passed away. But they also worked in causality. And a later paper by Kahneman and Miller made it quite explicit. They said, look, when people are thinking about counterfactuals, they're much more likely to change, to modify, to undo exceptional aspects of the causal chain rather than routine aspects. So if you think of the professor taking the pen as exceptional, because professors aren't supposed to take the pens, they're much more likely to undo those when considering counterfactuals, and thus will blame the professor. So we can formalize this by adding a notion of normality to the models. So it's actually normality on worlds and outcomes. And we can, in our notion of normality, we can take Professor Smith taking the pen to be less normal than the assistant taking the pen because Professor Smith broke the rules. We prefer to modify the world to make things as normal as we can. So what we change is the world where the professor took the pen, making that normal. He doesn't take the pen, and we declare him to be a better cause of the outcome than the admin. That means we have sort of a graded notion of causality. Let me skip the formal model so that I can finish in a reasonable approximation of noon and a lot of time for questions, but very briefly, we have a causal model just like before, but now we have in addition a normality relation on worlds, and we prefer a cause where the witness to the cause is more normal. The witness to cause is, we keep W fixed and change X to X prime to get the but-for causality. So that is a witness. You might have several witnesses, and the witness that makes things most normal gives you the best cause. That's the idea. But interestingly, so the question is, in the formal model, we don't tell you where the normality relation comes from. But of course, if lawyers were going to take our definition seriously, they would want to argue this is more normal than that. What does normal mean? So normality can mean statistical frequency. Things are more normal if they're more in accord with the typical statistics. We have, some notion of typicality. Birds typically have wings. It's normal for birds to have wings. Conformance to a norm, as in the example where the norm was the professors weren't supposed to take the pens. Moral obligations, thou shalt not kill. It's abnormal to kill. And it seems that people consider all these notions when judging normality. And it seems, I haven't done the experiments, but this is my impression from the experiments, the typicality trumps statistical frequency, conformance to a norm trumps typicality, and moral obligation trumps conformance to a norm. So for example, in the Josh Knobe example, typically professors and statistically professors took the pen, let's say, just as often as admins, but they broke the rule. So they're abnormal, even though as far as statistics goes, they're completely normal. So we think of the normality ordering as part of the model. Lawyers can argue over what the right model is. So among other things, they could argue about the normality relation. Different choices for the normality relation give you different outcomes as far as causality goes. All right, let me consider another topic, responsibility and blame. Now, the definition of causality can be extended to deal with responsibility and blame and lots of other things, explanation. So causality as it stands is a 0-1 notion. I mean, either you're a cause or you're not. We can easily extend this to talking about the probability that A is a cause. We simply put a probability in a context. So notice, in a fixed context, there's no probability at all. All the equations are deterministic. So the only place I have probability in causal models is on contexts. And now I can say, what's the probability A causes B? Well, I can look at all the contexts where A is a cause of B, and that's the probability that A is a cause of B. But I want to look at a different notion. I want to say that not all causes are equal. Suppose B wins an election against G, so this was written at the time of Bush and Gore, by a vote of 11-0. So you might say each voter for B is part of a cause of B's winning. But that seems to be very different from the case where the vote was 6-5. Again, each of the voters for B is a cause of him winning, but somehow they're more critical. So it's this notion of criticality that I want to get at in the notion of responsibility. They're somehow more responsible for the outcome. So we can have a voting example, we can formalize this. There are 11 voters and an outcome. Each voter either votes for or against, either for Gore or Bush, 0 or 1. And clearly, everybody who votes 1 is part of a cause for the outcome where everybody votes for Bush. But in order to get AC2 to hold, you really need 6 of them, right? For the cause is any disjunction of 6 voters. Because if you change 6 votes, you change the outcome in an 11-0 case. Now, in the 6-5 case, you only have to change 1 vote. So the idea of responsibility is to choose the smallest witness as a measure of degree of responsibility, right? The witness here is just any one of the voters is a witness for the causality. Here you need 6 voters. So roughly speaking, well, actually formally speaking, the degree of responsibility of X equals X for phi, well, it's 0 if X equals X is not part of a cause. When I say part of a cause, it's one of the disjuncts in a cause. So if you're not part of a cause, you're not responsible for the outcome at all. It's 1/k if X equals X is part of a cause with a witness W, and the K is the sum of the size of X and the size of W. So in an 11-0 vote, your degree of responsibility is 1/6, because the witness just has any 6 voters. If it's 6-5, the degree of responsibility is 1. Now, this is clearly a very naive definition, but it does seem to capture some intuitions. I'll come back to that. Okay, let me look at a related notion. That's degree of blame. So when determining responsibility, I've assumed that everything is known, right? You know what the world is, you know how the world works, you know the equations, you know the context. There's no uncertainty in the voting example about who voted for whom. But sometimes you want to take the agent's epistemic state into account. So imagine a doctor who uses a drug to treat a patient, and the drug, let's say, is the cause of death. The patient taking the drug actually caused the death. Well, in that case, the doctor giving the drug caused the death. The doctor has degree of responsibility 1. But what if the doctor had no idea that there would be adverse side effects? Then we might want to say that he's not to blame for the death. He is the cause, he is responsible, but he's not to blame. How do we capture that? Well, before I go into formal details, I should say that in legal reasoning, what matters is not only what the doctor knew, but what he should have known. So degree of blame is relative to an epistemic state. Here I take an epistemic state to be a probability over causal models and contexts. So you don't know how the world works. You don't know what the equations are, but you have a probability over them. That's a probability on causal models. And you might not know what actually happened. Who shot the bullet? So the epistemic state is a probability on pairs consisting of models and contexts, and the degree of blame is the expected degree of responsibility. So given a model and a context, we can compute the degree of responsibility. That was this definition. And now we take expectation with respect to this distribution. But which distribution do we use? One is that we could use the doctor's actual distribution, the doctor's actual uncertainty, or what the law says, at least American law, says you might want to take the distribution that represents what he should have known. So, for example, the doctor might, in fact, not have known that the drug had adverse side effects. So he assigned, let's say, probability 0, or very small probability, the drug having adverse side effects. But if he'd only taken the time to read the instructions that came with the drug, it said quite explicitly there, if the patient has this condition, there can be quite bad adverse side effects. So the doctor should have known. Or perhaps there was an article in a well-known medical journal that explained, showed that the drug could have adverse side effects. And again, the court might decide the doctor should have known that. So the distribution that's used is not the doctor's actual distribution, but the distribution that the court says is that of a reasonable person, a reasonable doctor in this case. Now, as I understand it, in American law, there's a difference between civil cases and criminal cases. That's certainly true. So if in a criminal case, I believe that the American law takes the doctor's actual epistemic state. So he wouldn't be criminally liable if you believed that the drug was okay, even if this article said that it wasn't. But as far as civil law goes, it's what the doctor should have known. Take that with a grain of salt. I'm not a lawyer, but that's my understanding. So the definition is open to both notions, right? Whether or not you're to blame is with respect to an epistemic state. The definition doesn't tell you which epistemic state to use. So let me give you an easy example. Imagine a firing squad with 10 excellent marksmen, and they do this kind of thing. Only one of them has a live bullet. The rest have blanks. The marksmen don't know which has the live bullet, so they assign probably 1/10, each of them having a live bullet. The marksman shoots the prisoner, he dies. Only one marksman is the cause of death, the one with the live bullet. Had he not shot, he wouldn't have died, but for cause. That marksman has degree of responsibility 1. All the rest have degree of responsibility 0. And therefore, as far as any marksman is concerned, each one of them has degree of blame 1/10, because that's just the expected degree of responsibility. Does that make sense? Questions? So let me mention a few computer science applications. I mean, clearly it's causality arises in legal reasoning and scientific reasoning. But if we care about things like accountability, there's a security breach. What was the cause? So people have used our definition to make sense out of accountability. For databases, you're interested in a query that you ask a query, you get an answer. Which tuple in the database caused that answer? So people have looked at that, and to make things tractable, they slightly changed the definition. But again, they were basically using our definition to define causality. What caused the network failure? People want to understand. My favorite example is perhaps program verification, where Hana Chockler, who was my co-author in the responsibility and blame paper, and various co-authors, looked at programs, and she was interested in program verification. She could see the program failed the spec. The program was incorrect. And she was interested in the question, which line or lines of code caused the problem? Which line of code is the most responsible? To what extent is a line of code responsible for the program? Because that's the lines that you want to fix. So based on our definition, she wrote a little program to figure out the degree of responsibility of each. These are finite state programs, to figure out the line of code that's responsible for the error. The interesting thing is, when she took down the software just to patch it, all the software engineers complained. They really liked it. They were using it. So I left out perhaps the biggest example these days, machine learning. So machine learning, we get lots of data, we get lots of correlations, but people these days are interested in causality. Can we figure out causes from all that data? That turns out to be hard, but again, causality comes in there very much. Let me say a few words about complexity. All the examples in the philosophy literature tend to be small, but you can imagine in CS we have applications that involve hundreds of variables. How hard is it to compute whether A is the cause of B? It turns out that it's D1P complete. D1P complete. D1P is a complexity class introduced by Papadimitriou and Yannakakis. It's those languages L that are the intersection of two languages, L1 and L2, where L1 is an NP and L2 is an co-NP. I'm assuming this audience, although it's a logic seminar, knows about P and NP. So where does the NP and co-NP come from? Well, the definition has three clauses. AC1, which just says A is a cause of B, if both A and B are true, can be checked in polynomial time. Checking if AC2 holds. AC2 holds says there is a W you can hold fixed. So that existential quantifier makes it NP, you guess the W. And AC3 says there's no smaller cause. So it's a co-NP question. The dual would be to say there is a smaller cause. That's an NP, because you can guess and verify. So the L1, that's the NP language, is all the formulas that satisfy AC2. The co-NP language is all the formulas that satisfy AC3. You want a formula that satisfies both, so it's in the intersection, and that makes it D1P. But if you have just binary models, so all the variables are binary, either 0 or 1, then it turns out it's NP complete. It actually simplifies a bit. So let me conclude with just a few words about practice. People don't always agree on descriptions of causality. People apply multiple intuitions. And nevertheless, experiments in Amazon Turk, which were done with Toby Gerstenfeld, which were done by Toby Gerstenfeld. Josh ended up being a co-author of the paper, Josh Tenenbaum, but it was mainly Toby. We would sit there and sort of try to think about experiments, about degrees of responsibility. And with Amazon Turk, it was amazing. Toby could call me back and after a couple of hours say, I've run the experiments, done. So it turns out that our naive notion of responsibility did predict qualitatively how people ascribe responsibility. But people's responsibility ascriptions are affected by normality. And the way we showed this was we considered things like there's a vote. It's a 4-0 vote. How responsible is each player? Well, our definition would have said a third, but and as opposed to if it's a 3-2 vote, how responsible is each player? And qualitatively, people did what our definition said, that the 3 who voted for were more responsible than in the 3-2 case, than let's say in a 3-1 case where but now the interesting thing is if we talk about Democrats and Republicans and we say the Democratic Party line is to vote for, the Republican line is to vote against. Now the vote was 3-2. One of the 3 was a Republican who voted for against the party line. The other 2 were Democrats who voted for. To what extent is each one responsible? The Republican who went against the party line did a far more abnormal action, was much more responsible for the outcome than the Democrats. And this should be consistent with the way we talk about things, in a vote in the Senate. We tend to look at the swing voters, the ones who might cross party lines, and focus on them, not all the ones who are voting according to party line. So these are just another minor comment is that the ascriptions of responsibility were also affected by prior probabilities. People conflated what we call responsibility and blame. Nevertheless, qualitatively, our definitions seem to be in the right ballpark. But let me just give you one more example and I'll stop. Depending on their focus, if you ask a question like, what is the cause of the traffic accident? People give different answers. An engineer might say, faulty road design. A mechanic might say, faulty brakes, bad brakes. A sociologist might say, oh, it's because you built a pub near the highway. The driver drank too much and then had the accident. The psychologist might say, oh, the driver just broke up with his girlfriend. He was depressed. That's why he drank too much and that's why he had the accident. Now, all these answers are reasonable. It depends, and we can capture them all. It depends what you call exogenous and endogenous. And the claim is that typically what we make exogenous is what we can't control. And what we make endogenous is what we can. And we're interested in causality because we want to change the world, but all we can change is what we can control. So the engineer might feel like they can control the road design. They make that endogenous. The mechanic can't control the road design, but he can do something about brakes. The brakes become endogenous. The sociologist might feel, what do I know about faulty brakes and road design? The pub, that's something I can think about. And the psychologist, of course, might think about, things like the driver's state of mind. So it shows how modeling can have a huge impact on the answer that you get. Now, I should say that we have a definition. Our first definition was shot down because Max Hopkins found a counterexample. How do I know that people won't find a counterexample now? Well, I know they're trying. Our paper's gotten quite a few references, I think over 1,000 at this point, and I feel like I'm walking around with a a T-shirt with a big red target on it, and all the philosophers are trying to come up with counterexamples to our definition. I don't think they've succeeded. They might think they have. But whether or not they have, I claim this is a useful definition. People, as I say, have applied it in the context of databases, machine learning, accountability, and so on. It seems to be useful. More importantly, or at least as important, the framework itself, the structural model framework, I claim is really useful. We've used it to define blame and responsibility. I talked about that. I could give a whole other talk about explanation, another one about blameworthiness, which is different from blame. Intention. To what extent, did you intend this outcome? Harm. These are all definitions, these are all notions that have been hard to define, and using structural models makes them much easier to define. But I expect that in the future, it's the applications that are going to drive the research agenda. I mean, right now I'm talking to folks at Google about explanation. They're really interested in causality because they're looking at recommender systems. So they want to make good recommendations to users. If they could understand the user's causal model, they would understand, be able to make better recommendations. And of course, they also want to explain their recommendations. And again, I would claim that if they had a good causal model, they could give good explanations. So, but the kinds of questions they're focused on are somewhat different than the ones I've considered so far. I think that's great. They have, really practical things they care about. And that might very well drive the research agenda in the future. So with that, let me stop. I'm open for questions, more questions. So.
Yep. Professor, thank you very much for your talk and presentation. It was really, really great. Yes, I think it's time for questions. So, dear participants, if you have some questions, you can just write it at the chat, and then I will read it, or raise your hand and say it. So, yeah, there was a question.
Thank you for your talk. I have maybe still a question, but it concerns the degree of responsibility. When you talked about it, all your examples dealt with independent actions of different agents. So my question is whether this model was maybe expanded or maybe somewhere in technical details, and I didn't catch it, to cases when there is some
If you had,
social dynamics or influence within the
if
group.
you had dependence, that would be captured in the causal model, right? So it could be
Yes, so how
I
you
vote the way that
determine,
you vote, right? So we'd have an edge from my vote to your vote,
yeah,
right? What causes your vote? And for degree of responsibility, for example, it
yeah,
would be enough to change my vote to also change your vote. So the definition absolutely takes that into account. I mean, otherwise it wouldn't be very interesting. It would work essentially the same way. It would just in a different causal model. So the causal model where they're independent is simply a different model from the one where they're dependent. And not surprisingly, you get different descriptions of responsibility in the two models. So for example, suppose, let me just give you an example. This will make it clear. The vote was 11-0 again, but I controlled 5 other people. That is,
yeah.
so now if you change my vote, you change all 6 votes, and I have degree of responsibility 1, not 1/6, right? Because in that model, if you change my vote, that's enough to change the outcome, even though it was 11-0.
I think I should just later look into the technical details, but I'm somewhat hesitant about the combination of dependence between agents' actions and the cases of preemptions, because
Okay,
for
well,
conditional
something
but for
saying-
you need to fix something, but if
Yeah, so-
there is codependence, so seems to be
Yeah,
a
I
problem
understand what you're saying.
usually.
It would be interesting to come up with a few examples, but probably it's best done offline. But if you think
Yeah.
about it offline and have questions, don't hesitate to email me and
Yeah, thank you. And I have a second question as well. I know that model logics and more importantly, and not more importantly, but more widely used, there are some game theoretical models which are used for ascribing the degrees of responsibility and for modeling casual, господи, causal relations between agent sections. Is there some sort of correspondence between such game theoretical models and your causal models?
so what kind of game theoretical models you're thinking of? I'm
Game
fairly familiar with them.
theoretical approach.
I mean, who are you think? I mean, which researchers? I'm
Uh,
fairly familiar with
Braham, Van Hees,
Bracha.
Braham and Van Hees, two authors from
Oh, okay.
Netherlands, I think. Yeah.
Yeah. They're looking at causal ascriptions in a multi-agent setting,
Yeah.
and we have definitions not so much of degree of responsibility in a multi-agent setting. I think that would actually be interesting, but of a notion called blameworthiness, which again, the intuition is
Yeah, no, but there was
Yeah.
a model proposed where you can extend it quite intuitively. The article is called An Anatomy of Moral Responsibility, as far as I remember.
Yeah. So
there is something similar
I've
there.
read the paper. I don't think it quite does it right, but I agree that there could be game theoretic considerations, and you'd have to capture that in the causal model, the effect of my actions on yours. And actually, to make it more complicated, if you really want to take game theory into account, you'd have to talk about beliefs. What do I believe
Yeah.
going to do? Which I don't think the Brown paper does in a serious way. We do have a notion of group blameworthiness, and then use an idea from game theory called a Shapley value to assign individual degree of responsibility, which I think is actually closest the questions we're looking at are closest in spirit to the Brown paper. But that's not game theory exactly. It's as I say, once we've figured out, we sort of treat each group as a single agent first, and then say, to what extent can they change the outcome? Once we've figured out a degree of what we call blameworthiness for each group, now we're interested in ascribing blameworthiness to individuals within the group. And then we're interested in sort of the credit assignment. And for that, we use Shapley value. And that's sort of what Brahm and I forget his co-author's name are interested in. Yeah, right. That they want to do a credit and blame assignment. To what extent does your action make a difference? And I would argue that Shapley value does actually a reasonable job of capturing that. So to some extent we did that. We might not have covered all the ground that you want us to cover, but some more
Thank
research.
you.
Sure.
So the commentary in the chat. The other important application could be building good performance benchmarks, because it's really easy to introduce some unexpected causes to actual results.
So I'm not sure I understand the question.
I think it's just a commentary in the chat.
Yeah, no, I see it in the chat. We
So-
certainly, So the claim is we could use causality to build performance benchmarks. I think that's true. And is the point that to really build them well, you need to understand the causal model because, some combination of causes could lead to unexpected results. So when you're building your performance benchmark, you'd have to take that into account. If that's the question, or if that's the comment, I certainly agree. But I'm not sure that I have anything to add. It does suggest why it's not easy to build a good causal model. Because if you really wanted to test all the combinations of actions, and you had a large number of variables, it's exponential. What might make things more tractable, and we're looking at questions like this now, is if you assume up front the causes can never be too large. That even though it might be an unexpected combination of events, it's not an unexpected combination of 100 events. It's an unexpected combination of 3 events. So if you keep things down at the 2 or 3 or 4 level, it might be tractable to build a good causal model.
So, I also have some questions. They're kind of philosophical. So the first one concerns the concept of randomness. So how do you understand it? And do you associate it with probability theory, or how can it be accounted for in systems of equations?
That's a good question. So our systems of equations don't have probability. All the probability goes up front. There is some loss of generality to that. That is to say, you can convert a system that intuitively has probability on the edges and bring all the probability to the top, to the context, but you do lose something in doing that. People have looked at what are called causal Bayesian networks that do have probability on the edges. I have a recent paper that talks about when you can convert that to a regular causal model with probability only on the outcomes. Now, that doesn't answer the question philosophically, how do I think of the probability? That depends on the application. So the model doesn't care. The model just says there's a probability. Now, is the probability subjective probability? Is it somehow an objective probability? I think that depends on the application.
Thanks. And so can we say that your system is kind of deterministic, had a deterministic structural equation?
Yes, I mean, it does, and there's no question. There's no probability in the structural equations.
Yes. So the second question is, well, your approach to defining actual causation, as you said it, has been applied in high-level domains like computer science, or as I know, in economics. And however, at the level of fundamental physics, so the world appears to be governed by the
By quantum.
yes, probabilistic laws of quantum mechanics, as I
So
know. So how
I-
does your theory of causality, which
it
is
does.
one
That is why I say
indeterministic, yes,
explicitly,
yes,
these
yes.
models can't handle quantum phenomena. I think it's an interesting question. Some of the work that I said I did recently on causal Bayesian networks might help to untangle that. You can think of it more as a what's it called, a many world phenomenon. So the claim is in quantum mechanics, or one approach has been that it's actually deterministic, but there are multiple worlds. That's more like what we're doing, but truly quantum, you really can't get rid of the probability on the edges. The definition simply does not take that into account. And there is some loss of generality in doing that. I
So-
talk about
And that the right concept of causation, as you define it, to remain coherent at the level, at that level, or is it an emergent property that only appears at higher levels of complexity?
Good question. So the idea of pulling all the probability up to the top sort of is related to thinking of you're playing against an adversary. And you can think of all the different strategies of the adversary, and you're putting a probability in adversary strategy. That really does cover a lot of cases. I don't think it really covers the quantum case seriously. I'm not sure I would think of it as an emergent phenomenon. It would be, if I understood the quantum case well enough, which I don't, there might be some result that says that if you start looking at the macro level, you don't lose any generality in moving the probability to the top, even if you do lose some generality at the micro level. But I haven't proved such a theorem, and I honestly don't know enough about quantum mechanics to even state such a theorem.
Thanks. And the last question's kind of technical. So, as I know, the really popular temporal logic approach to causation. And what do you think about it?
Well, I mean, I'm quite happy with with saying that causes must precede effects. So if you add time, you'll get that phenomenon. I think other attempts at defining causality just using temporal logic fail. They just don't capture all the subtleties. I am very interested, as in I am currently writing a paper on defining a modal logic of belief, time, and causality. And what turns out to be particularly interesting there is not the temporal component, which is quite straightforward, but the belief component, because we want to allow interventions on beliefs. I'm an advertising person, and I can say, well, if I could convince you to believe X, if I could somehow intervene and get you to believe X, then something would happen. So we have interventions on beliefs, and giving semantics to interventions on beliefs while maintaining the properties of beliefs, in our case, for modal logicians KD45, turns out to be non-trivial. So getting a good model of causality, belief, and time, but as I say, the time is not the real difficulty, turns out to be quite non-trivial and interesting. But I'm not sure I've answered your question. We keep our definition of causality, though. So it's not that we change the definition of causality. The model enforces the fact that causes are temporal in the sense that only earlier events can cause later events. But that's a semantic consistency condition that we impose. And and again, it doesn't change the definition of causality.
Thank you. So, is there any other questions? No. And I think that's all. So, Professor Halpern, thank you again for coming
You're
and
welcome.
joining us. It was pretty nice. So,
Okay.
thank you. Thank you again. So, have a nice day and
You too.
good luck.
Nice evening in your
So,
case.
bye.
Bye-bye.